Let's take a closer look at the Swift programming language. This lecture assumes that you have object-oriented programming experience, but does not assume any prior experience with Objective-C, Apple's older language. Swift is a powerful new language created by Apple and released in 2014. It works side by side with Objective-C codebases and has a syntax that's a lot closer to other popular languages such as Java and Python than Objective-C had. This means that it's a lot easier to pick up for new developers, and it is the primary language we will be teaching for iOS programming. The first thing that we want to look at in Swift is how we declare variables. In Swift, we have two keywords for declaring variables, var and let. We use the var keyword when declaring a regular variable. This is a variable that can be changed after declaration. But we use let when we are declaring a constant. Constant variables cannot be changed after they're originally set. In Swift, it is generally best practice for you to camel case your variable names. This means that the first word of a variable name is lowercase, and every word after that is uppercase. So if we say var variable number equals 5, then we can change that variable later on. But if we say let constant number equals 3.14, then if we try to change constant number later on in our code, we will get a compiler error and not be able to do it. You may have noticed in the last slide that we did not have to explicitly declare a type for our variables. Swift is still a strongly typed language, which means that when we said var variable name equals 5, if we changed variable name, we could only ever change the value to another integer. But Swift has something called type inference. Type inference means that when you don't explicitly tell the compiler what type of variable it is, it'll do its best to infer its type based on the initial value. So this means that we could say var explicit variable int equals 10. This would be explicitly declaring the type, and the compiler will definitely get it right because you told it what you want it to be. But we could also say var inferred variable equals 10. The compiler is going to look at the initial value of 10 and decide, oh, this should be an integer. But what if we really wanted it to be a double? Then giving an initial value of 10 wouldn't be enough. We would have to say var explicit variable 2 double equals 10. This tells the compiler that despite the initial value looking like an integer, we want it to be treated as a double. Swift also has this really weird concept of optionals. So when we declare a regular variable with a regular type, it must always have a value. That value can never start off as nil and never be set to nil later on. But Swift introduces optionals to allow values to be nil. What an optional says is this variable may hold a value, or it may hold nil. Optionals are denoted with a question mark. So as an example, if we say var always an int, int equals 15, then if we tried to say always an int equals nil, the compiler is going to stop, give us an error, and not let us compile from there. But if we said var maybe an int, int question mark equals 15, we've declared maybe an int as an optional integer. This means that its value could be nil later on, so it's completely valid for us to say maybe an int equals nil. It would also be completely valid for us to declare maybe an int without giving an initial value. The inclusion of optionals in Swift is one of the reasons you'll sometimes hear people say Swift is a very type-safe language. Optionals force you to think ahead of time of how you're going to use your variables and what sort of values they can hold. When you use a regular type, you are promising yourself that anytime this variable is accessed, it will always have a value. But if you know that your variable might be nil at some point, then you're forced to use an optional, which means that you have to treat it differently when you access it. You need to check if its value is nil. So it's a way of reminding yourself, hey, this might not actually have a value. In a lot of other languages, this leads to bugs that are very tricky to debug later down the road. So Swift having optionals is actually a great thing. It's a little bit more work up front, but it'll save you a lot of time later on. So how do we actually use optional variables? Before we actually use them, we have to do something called unwrapping the optional. So to do this, generally what we'll do is check if the optional variable contains nil with an if statement. If it doesn't contain nil, then it's safe for us to forcefully unwrap that optional. We forcefully unwrap optionals using an exclamation point or a bang, depending on what you want to call it. Let's take a look at an example. If we did not have an if statement here, we could be forcing our program to crash, because when you forcefully unwrap an optional that contains a nil value, then your program receives a runtime error and crashes immediately. So what you have to do to be safe is always check for nil on an optional prior to forcefully unwrapping it. Now, you might be looking at this example and thinking, this syntax looks really dirty. There must be a better way. And there is. We call this better way optional binding. It's a cleaner way to unwrap optionals. It binds the value of an optional to a new variable if and only if that optional did not contain nil. So we still use an if statement, but this time we give a new variable name, and if we enter that if statement, then we know for sure that the optional had a value that wasn't nil, and we can access that value with this new variable name. So inside this if statement, we can always say definitely an int and treat it as a regular type, a regular non-optional variable. And we know that its value is always there. Swift also has a concept called implicitly unwrapped optionals. These are kind of like optionals in the sense that they're variable types that could be nil, but this time they're not going to give you a compiler error if they're ever set to nil. It's only going to trigger a runtime error if they're accessed and the value is nil. Implicitly unwrapped optionals are denoted using a bang or exclamation point. So if we give a variable a type of string exclamation point, then we are creating an implicitly unwrapped optional of type string. This means that its value could be nil, and we're not going to worry about it at compile time. We're only going to crash at runtime if we access it when it's nil. So if we later on try saying string length equals count, always a string, when string has nil in it, it's going to crash at runtime. So this means that the responsibility is back on us as a programmer to kind of try and keep everything in our head as to whether or not we should be checking this variable for nil. Implicitly unwrapped optionals we're going to use generally for code connections and things that we know that we want to immediately trigger a crash if they're broken. So this will make it a little bit easier on our end to debug because we'll notice that these values are nil earlier on as soon as we try and access them. But they can be very dangerous if used incorrectly. There's one more important concept pertaining to optionals that we want to talk about. This concept is called optional chaining. Since we know that we cannot access an optional without unwrapping it, there has to be some sort of clean syntax for doing it all in a single line. Optional chaining allows us to do this. It allows us to access a variable or call a method on an optional only if and only if that value of that optional is not nil. So say we've got a variable optional array. We know later on in this code that since it's an optional, it may contain a regular array or it may contain nil. Say we want to get the count or the length of this array if and only if it exists, and we want to do it all in one line. We can say var array length equals optional array question mark dot count. Now, if optional array contains nil at this point in time, then array length is going to be nil because you can't count in nil array. But if optional array is not nil, it actually contains an array, then array length is going to contain the count of that array. So it'll contain an integer. This means that array length would have to have a type of integer optional because we don't know necessarily whether or not it is nil because we optionally chained count onto optional array. So we're done talking about optionals for now. Let's move on to this array syntax that we just showed you. In Swift, arrays can only contain a single type. So that means you can't have an array that contains some strings, some integers, some other objects. If you create an array for strings, then it's only going to contain strings. The let keyword and the var keyword both come into play for arrays. Let will make an immutable array. This is an array that cannot change once it's been created. Var, on the other hand, will create a mutable array. These are arrays that you can append to, that you can change values of. The pros and cons of using immutable or immutable arrays are beyond the scope of this lecture. We just want to let you know that when you use let to declare an array, it creates an immutable array. And when you use var to create an array, it creates a mutable array, or an array that you could change later on. Swift provides all sorts of convenience methods and properties on arrays, things such as count, which will return the number of items in an array, is empty, which will return whether or not an array is empty, append, which will allow you to add a new item to the end of an array, and insert, which allows you to add an item anywhere within an array. So you can say insert new string at index 5, and it's going to go to index 5 and put that new string into an array. let's take a look at this in practice. When we say let grocery list equals open bracket eggs, comma, milk, close bracket, we are creating an immutable array. This means that we cannot change any of the values of grocery list, and we cannot append to it. This array is set, kind of frozen in time. But if we say var, the keyword being var versus let, when we say var mutable grocery list equals eggs, comma, milk, then we are creating a mutable array. We can change the values of this array later on. We can append to this array to change its size. Just in case you didn't notice the other difference between example 1 and example 2, I want to point out that arrays, just like other variable types, can be inferred by the Swift compiler. We can explicitly say that an array is of type string, like in example 1, or we cannot say it, but that does not mean that we can store other types in a mutable grocery list. Mutable grocery list is going to be inferred as an array of strings. This means that despite not explicitly declaring the type for a mutable grocery list, if we try to add an integer to it later on, the compiler is going to stop us. It's going to say, whoa, whoa, whoa. This is an array of strings. You can't add an integer to an array of strings. Accessing a specific element of an array looks a lot like it does in other languages. We give the variable name of the array we want to access, and then inside brackets we put the index of the element we want to access. And Swift has a 0-indexed array system, so that means that this example here is accessing the first or 0th element of the mutable grocery list array. This means that item is going to be set to eggs. In addition to arrays, Swift also has dictionaries. Dictionaries hold key value pairs. This means that for each value in a dictionary, there is a key that you use to retrieve it. This concept is a lot like dictionaries in the real world. In a real-world dictionary, the key would be the word itself, whereas the value would be the word's definition. A lot like arrays, dictionaries are singly typed. This means that every single key needs to be the same type, and every single value needs to be the same type. So you can have a dictionary that goes string to string, or string to integer, or integer to string, whatever you want, but all the keys need to be the same type, and all the values need to be the same type. You should also keep in mind that it is best practice to use optional binding when accessing values in a dictionary. This is because if the key does not exist in the dictionary, then the value that is returned is going to be nil. So to be totally type safe, since we're getting an optional back, we really do want to use optional binding. So let's look at some examples. When declaring a dictionary, it looks a lot like an array, except there's two parts to each element. There's the key and the value. The key and the value are separated by a colon, and then each key value pair is separated by a comma. So now that we have the cities dictionary declared, say we want to access a value in that dictionary. So we're going to say cities, open bracket, pass in a key, close bracket. In this case, we want to access the value associated with the key of London. So if we say cities, open bracket, London, close bracket, it's going to return the optional string value of UK. Later on, say we want to remove the key value pair of London, UK from the dictionary. To do this, we're going to say cities, open bracket, London, close bracket, equals nil. And by setting the value to nil, the key value pair is removed from the dictionary. Now that we've introduced the array and dictionary data structures in Swift, let's talk about control flow in Swift. There's not a whole lot to say about if-else statements in Swift, but that's mainly because they're a lot like if-else statements in other languages. The one thing to point out is parentheses are not actually needed around the conditional that you're checking for. So we can just say if is human instead of saying if open parentheses is human, close parentheses. Swift has two types of for loops. It has for in loops, which are used to iterate over arrays and ranges, but you can also use traditional loops if you prefer. So in our first example, we are iterating over the range 1, 2, 3. By putting ... between two integers, we are creating an inclusive range. Had we used ... less than, then this would have been a non-inclusive range. It would just be 1, 2. But in this case, it's going to print out I can count to 1, I can count to 2, I can count to 3. In our second example, we are using a more traditional for loop by setting our iterator, setting our conditional, then setting our incrementer. And again, this is going to print out I can count to 1, I can count to 2, I can count to 3. When talking about functions in Swift, the main thing to point out is the type and name of arguments are backwards when compared to most other languages. The name of the argument comes before the type. So, in this example, we are declaring a function named difference that has 2 arguments. The first one with a name of num1 of type integer, the second with a name of num2 and type integer, and then it returns an integer. We know it returns an integer because there's a little rocket and then int. The syntax for calling this difference function is similar to a lot of other languages. We just give the function name, then the 2 arguments with comma-separated values. Something that Swift inherited from Objective-C is the use of external names for arguments and functions. Say we wanted to declare a function called resize that took in 4 arguments, width 1, height 1, width 2, height 2, all of type integer. This resize function, when we call it, would have comma-separated values. Now this works out. A lot of languages like Java, this is exactly how you would do it. But it's not ideal because when you look at this code later, and without looking at the definition of resize, we're not entirely sure which of these arguments is which, what they're associated with. To fix this, we can force the programmers to use external names. When we declare a function resize2, we have not only an argument name, but an external name. So the format is external name, argument type. So in this case, when we call resize2, each argument has a label before it. In this case, it's resize2 from width, argument, the first argument, from height, the second argument, to width, the third argument, to height, the fourth argument. So by using external names, it's a lot easier when we read the code to know what the arguments are actually being used for. There's no way to look at the resize2 function that we're calling and not know that the first argument is the from width, the second argument is the from height, and so on and so forth. Now you might think, oh, this really sucks, I have to type a lot more in Swift. But if you haven't noticed yet, the code completion in Xcode is pretty phenomenal. So you start typing resize2, you select the function from the code completion menu, and it will automatically fill out these external names for you. You just tab through each argument, put in the actual argument you're passing in, and you don't have to type anything extra. External names allow Swift code files to be somewhat self-documenting, and it makes it a lot easier to read through code bases without constantly referring back to documentation. The last thing that we're going to talk about today in Swift is classes versus structs. Classes are passed by reference, while structs are passed by value. So what does this mean? That means say we've got a boat class. We say var coolBoat equals boat. Then we say var someBoat equals coolBoat. Now, if we change anything on coolBoats, like say set its speed to 30 miles per hour, then since someBoat contains a reference to the same memory space as coolBoat, then the speed on someBoat is also technically changed. On the flip side, say we have a size struct. So we say var coolSize equals size, then var someSize equals coolSize. Now, if we were to change coolSize, it would have absolutely no effect on someSize, because coolSize is a size struct, which means that when we said someSize equals coolSize, we had copied all the values of coolSize and created a new struct with those same values for someSize. So these two are now independent of each other and have their own memory space. So that pretty much wraps up the core basic concepts of the Swift programming languages that we wanted to talk about. If you have any questions on these concepts, be sure to check out the playgrounds that we created to go along with this lecture, and also check out the Apple documentation. The Apple Swift documentation goes very in depth on all these concepts and much more.